小了一点。
他讲了那个。Hello, testing. Since not many people are coming, you guys have assignment or a lot of assignment? Yes. Okay. Understand. We can discuss again on Thursday. You try first. Okay, we discuss on Thursday about the extension, Discuss, but no, I mean discuss again when we extend. But even if we extend, right? I don't think we can extend assignment 3 anymore because we need to have midterm soon, and then after midterm will be assignment 4, and then 5, 6, 7, 8, and then 5. Okay, yeah. Right. So yeah, I found this quote by Edison. Like we talked about it this morning. Okay. Actually, Edison is not an inventor. Actually, he's a businessman. He's still Tesla idea. So Tesla is the original inventor. Yeah. Okay. Anyway, let's clean up something that we have this morning. So this morning, remember that we did we prove a statement that if X has an order n, then Sm is what? Sm is really just Sm mod n. Okay. So how should you think about this? How should you think about this? Really, we need to have introduce division algorithm. Do you still remember what a division algorithm is? This is primary school stuff, right? So before I translate for you, what's this statement here? So if you take a positive integer, okay, positive integer, and then you take any integer, then what do you have? You have a unique integer called the quotient, I guess, and a remainder, okay, such that what? You can write n equals to a q multiple of m plus this remainder. What's this remainder? This remainder should lies in what region? Should lies in 0 to m. Remember or not this one? Example, need example or not? For example, 2除10，10除2。Okay, maybe 让它除不断，3，10除3。Okay, what did you get? 3, 9, remainder is 1. So in this theorem here, what can you write? You can write 3 as, you can write 10 as 3 times 3 plus 1. Okay, so this is the division algorithm. So in our case here, what is this m mod n? So this for here, so here we can define R is equals to what? R is equals to n mod m. Okay, so this is by definition. Okay, so by definition, this is the remainder you get. So to prove this blue statement here, what do? You first need to write m as what? You first need to write, so there exists, let's say, p and r, such that what? Such that m equals to p times n plus r, like that. So in this case here, what do you get? X to the power m is really what? X to the pn plus r, which is what? S to the pn times x to the r. But what is s to the pn? Identity, right? Because how many Sn you have? P of them. Okay, so this is really just, if you want to do computative commute, NAP also can. Okay, and really, what is this? This is just SNP times. Okay, which is just identity to the P times time XN if you like. Then what is that? It's just identity times XN. I just simply write everything. Okay. So I mean, these are R. Okay. And we define this R to be N mod N. Does it make sense? This division algorithm later we'll use again. That's why I want to introduce now also. Now I will use this division algorithm again later. So inside this division algorithm, right? This is a very important thing here. This Q and R is really unique. It's unique. Unique, you know what it means? Unique. There's only one Q and one R that satisfy this equation. This is what you did in your primary school. This 3 and this 1 is unique to 10 and 3. Unique. Right. Okay. Any other thing we need to clear out? Oh, okay. How Tian say you can find other solution of Artin in various website, people's website. That's true. That's true. Okay. But what they do is sometimes they didn't finish all the question. Okay. The other thing is those solution maybe has defect. Okay, maybe has defect. So you can go and refer, but I encourage you to try yourself. Okay, after you try, you can come and discuss with me. Okay or not? Please try and do a tutorial question. Assignment question is not enough for you to learn the theory. Okay. Basically the assignment is what I want to test you whether you know some skill or not. Okay. So if you look at all my question, right, I would like to test your understanding. Okay, so you need to understand what I teach or what I wanted you to know. Okay, no. So that's why I will sometimes go slower when I try to teach new stuff, so that you can have more times to think, and also you can ask me. Okay, does it make sense? Okay, so you need to stop me if something is getting hard or getting too abstract or getting uh, uncontrollable. You need to stop me. Okay, then I will know that, oh, this part you don't know, then we need to spend a little more time. Does it make sense? Okay. So as time go on, of course, we'll go a little bit faster so that we know each other pace, then we can go a little bit faster. Okay. Yeah. All right, so we should continue. So what statement we left? So the last statement we proved was if S has order n, we can reduce the cyclic subgroup, right? We can reduce the cyclic subgroup to what? To a finite set. To a finite set. But what's the cardinality of this set here? Exactly n. Okay, it's the same order as your generator. So let's make these precise here. So inspired by this proposition, we'll define the following. An element A of a group G. Okay, we said that it generates. Okay, again, we define this. Generates G and is a generator. Okay, generator for G if what? If you just look at the subgroup generator by this A here, it is exactly equals to G. Okay, and then in this case, we will call our group a cyclic group. Okay, because it is generated just by one element here. In particular, we have seen one example of cyclic group, right? Do you still remember this morning? I gave you an example of cyclic group, which is what? Sorry? Yes, good. It's the integer. Who generate integers? 1. So you use 1, you can get all the integers. Do you know how to get? First of all, you add 1 to itself. You will get all the natural number. How about 0? by definition is in there already. Okay. And then how about negative integer? These are the inverses, okay, for all the natural numbers. Okay, so you'll get the whole integer just by 1. So this is the first cyclic subgroup you see. Where is it? If there exists, this one.
Right, please.
This one? If there exists A in G.
Yeah, you know what? That hard. Generate one. Don't.
Oh, okay. Generate G. So yeah. Okay. GG. Okay, generate G. Okay. So this is talking about one generator, right? So we similarly like last time we can talk about multiple generator. So if, so definition, if there exists a finite set AI that generates G, okay, meaning what? That is G equals to the subgroup generated by AIs. Okay, then we will say that G is finitely generated. Okay? Because you just need finitely many elements to get everything inside a group. Okay, finitely generated. Does it make sense? Okay. In particular, Z is finitely generated because you just only need one element to generate. But if it's just one element, we have a special name. It is a cyclic group. Okay. Does it make sense? Okay. Okay. All right. Next. So next property. So what's the next property here? So theorem. Actually, every cyclic group is abelian. Okay. So this means what? If you know that your group can be generated by one element, right? You don't need to ask whether this LLC is commutative or not. It must be abelian. Okay. So how are we going to prove this? How to prove something is some group is abelian? What do you need to show? For every xy inside the group, you need to check that sy equals to yx. Okay, so this is what you need to check. Okay. So how? General xy equals to yx, not in this case here. How to show it? So let's prove it. So let's start with a cyclic subgroup. Cyclic group. So cyclic group by definition is what? Equals to what? Generated by one element. Okay, generated by one element. Like this. Then this means what? Do you have control of how does the elements looks like inside this group? Do you have control? You know? You don't know? You sure you don't know? What's if I give you any element M inside this G, how does M looks like? X, you're right. Some multiple. Some product of X. I don't know. Product of X. X to some integer power. Okay. So then every elements, okay, in G can be written as a power, let's say x to the power n of x. Okay. Of this. Amen. Then what do we need to check? So we need to check that for every nm in Z, what happened to xn star xm? And then what's our goal here? We want to show that Sn star Sm equals to Sm star Sn. But what happens in the middle here? What happens? Do you remember what's the notation of x to the power n or not? You compose n times, right? So here altogether you compose how many times? M plus n times. But the bottom, sorry, this one too quick swap already. M plus m. The bottom, x to the m plus n. But n plus m and m plus n should be the same. Okay, so we somehow reduce the question of commutativity in this group to what? Commutativity in Z. Okay, so this is a nice thing about cyclic group. Okay, the power will control the composition. Okay, so this is true by commutativity in Z. Okay, so this shows that G is abelian. Okay. I don't even need to know whether this star is addition or not, multiplication or not, or some other composition or not. No need. Okay. Maybe you started with a non-commutative LOC. Okay, but if you just look at a cyclic subgroup, it is abelian always. Does it make sense? Okay. Question? No question or not? Okay. Need example or you okay? Okay. If you're not okay, go back and try this subgroup. Let's look at S4. Okay, look at S4 and then look at let's say maybe how about you try S3 and then look at this subgroup here. The group generated by 1, 2, 3. Okay, see whether it's abelian inside or not. Okay, I think this group contains what? Identity 1, 2, 3 and 1, 3, 2. Seems like quite trivial in this case. Maybe we make it bigger. Make it bigger how? This one quite trivial, right? Because they are inverses of each other. Already commutative. Quite trivial. Maybe look for a larger one. Let's think. What's the larger thing? Maybe look at 1, 2, 3, 4. How about this in S4? Yeah, look at this. Is the composition there abelian or not? Yeah, try. Try yourself. Try at home. Convince yourself. Okay. So let's go on. Yeah, sorry. 1, 2, 3, 4. Yeah. So look at the cyclic subgroup generated by this. Let's see if the composition inside there is abelian or not. So question? Any question? Okay, feel free to stop me if you need some clarification. Okay, next. We can also ask about what is the subgroup of a cyclic group? Okay, it turns out that if you look at the subgroup of a cyclic group, it is still cyclic. Okay, meaning what? If I go into a cyclic group, okay, and then I consider any subgroup inside there, I can generate that subgroup using one element. Okay, so this is what we're trying to prove. You agree or not? 潘兴又在那边要问东西啊。潘兴 don't agree let's think So for example let's convince you first. So we know Z is cyclic, right? Okay, find a subgroup inside here. Non-trivial subgroup. What's a non-trivial subgroup you can consider here? 2, right? So 0, let's say 0, 2, 4, 6, like that. And then you take LLC, close under LLC, close under taking inverses. So these are the even number, for example. Okay, so these are the even integer. Okay, form a subgroup. Actually, we call this, okay, later I will disclose to you. So is this a subgroup or not? You agree this is a subgroup? Identity inside here, inverses, got. And then if you do addition, is it still get all the even integer? Okay. So the claim by this theorem says this is cyclic. Do you know who generated this set here? Huh? 2. Good. 2. So this is generated by the single number 2. That's why sometimes people will say this thing is called 2z. Present the even integer. So let's prove this. Okay, so let's prove this. So how to prove this? So this statement is about any subgroup. So you need to start with arbitrary subgroup here. So let H be a subgroup of a cyclic group. Okay. What could this subgroup be? What are the possible cases you will have? We will always have trivial subgroup inside our group, right? So maybe this H could be the trivial subgroup. But trivial subgroup generated by one thing, right? Which is itself. Okay. You just use E to generate this trivial subgroup. Does it make sense? Correct or not? You just use E, right? Where there's really only one thing there. You can take inverse, you can take LOC, E times E, whatever many times you want to times together. And then you can do, what else you need to do? Inverses. Identity is itself already. Okay, so this is easy, but let's say H is not equals to E. Okay, what happened? H is not equals to E. Okay, so if H is not equals to E, that means what? There exists something else inside H such that A is not the identity. Agree? Okay. Because subgroup must contain identity, right? Okay. And then what? Then we will do a trick here. Okay, do a trick here. We can pick the smallest positive integer, the q, such that a to the q is in H. Smallest one. Is it? Okay. Let me see. Am I doing something weird or not? Okay. Okay. Not convinced. Wait, what am I doing here? So, I mean, let's continue first, see what I'm going to do. So, our claim is, let's see this word or not. AQ will generate H. Okay, so this means what? H is equals to subgroup generated by this single generator here. So now, so let's prove this claim here. If we prove this claim, this means this H is generated by a single element here. Correct or not? Okay. So let's check. So suppose A to the N is another element in H. Okay. To show this generating by one element, what do you need to do? you need to show that for every element in H, okay, you can write it as a product of AQ. Okay, you need to write as a product of AQ. So suppose AN is another element in H, then we will see that N have to be strictly greater than Q. Why? Because we assume Q to be the smallest integer. Okay, if there's another A to the N exists inside there, N have to be greater than Q. Okay, agree? Okay. But what? But by division algorithm, division algorithm, what does it tell you? It tells you that we can write N as what? As a multiple of Q plus some remainder. Okay, like the trick we did at the start of the class. And then this means what? Because we know that, what do we know? We can write this further, right? This is equal to MQ times AR. Sorry, AR. Okay. So what do we see here? Not that, what happened? After division algorithm, right? What's this R? R have to lies in between what? 0 and Q actually. Strictly less than Q because it's a remainder. But can A to the R exist inside this set or not? Cannot, because this is the smallest. Okay, smallest, where is it? Because AQ is the smallest integer Q such that AQ is in H. Okay, so this means what? So this can be 0. So not that this is true by assumption on smallest Q, we must have what? R equals to 0. Okay. Otherwise, it will contradict that Q is the smallest one. Correct or not? Otherwise, this AR will stay inside my set already. Then contradict the choice of Q. Okay. So R have to be 0. So R to be 0 means what? Hence, we can write any elements in H by what? By simply composing AQ multiple times. Okay. Okay. Composing AQ with exerve multiple times. Yeah, no? Does it make sense? Yeah. Because our R is 0 already. So we can write AN as a multiple of AN. Okay. Any question? No question? No? Yes? What's random? What things is random here? Entry. What do you mean by entry? You mean this subgroup is random or? Yeah, it's random. Okay, so maybe there's one ambiguity point here. Why AN is another element in H? I don't know. Because why? Because we started with a cyclic group. So in other words, this is a special A actually. I think this A has to be the generator of my group G. Does it make sense? So this A actually is the generator of the cyclic group you started with. And then you consider the any subgroup inside. Does it make sense? So I mean, if you apply the story of this proof to this question here, you can see that if I write my Z as generated by 1 here, okay, then what is this? What's this smallest Q here? What's the smallest Q for this subgroup here? 2. Does it make sense? The smallest positive integer such that 1 to the some power is in this set, which is 2. Okay, so this guy, so by the method of the proof, I would say that this is generated by 1 to the power of 2, which is 1 plus 1 in this case. Okay, no? It's the smallest positive integer such that 1 to the q is inside the subgroup. Okay, no? It's the smallest one, right? You obviously also have 1 to the 4 inside this subgroup, right? But we pick the smallest one. Okay? Make sense? Okay, yeah, so whenever you don't understand proof, right, I suggest you cook out an example to see how the proof works. Okay, it must work one. Okay, otherwise the proof you can throw into rubbish bin. Okay, it must work on examples. Does it make sense? Any question? Okay, good. Okay. 你有 question 来？You mean prime number inside here? Sure. 2 is a prime number. Does it form a group or not? Does prime number form a group or not? All right. So if you include your subgroup, if your subgroup include all the prime numbers, I think somehow you will get back the whole group. Because 3 minus 2 is what? 1 already. If 1 is inside your subgroup, then you should generate everything already. Now I tell you a trick, a technique, how to see what group you generate. If you found the generator inside a group, you will generate everything. Once you found a generator inside a group, you found the whole group already. No. This is a trick we will use in some question. Okay. Okay. So okay, good. So corollary. Okay, so this is a very good corollary here. So the subgroup of Z, okay, under addition are precisely what? Precisely the group of multiple of n. Okay, multiple of n. How can you see this? How can you see this? So we know that. So okay, let's quickly say about this corollary here. We know what? We know that Z is cyclic, right or not? We even know their generators is just 1. Okay, it's cyclic. So by previous theorem, what do we know? All subgroup of Z is cyclic. Okay, all subgroup of Z is cyclic. Okay. So what are these subgroups? So these subgroups are precisely what? 1 to the sum power n, which is equal to what? N. No? Okay. These subgroups are this guy for all n. 哪一个? Which one? So wait, let me see. NZ. Yeah, NZ. No, it's a different thing. So just now, remember, just now we have 2Z as the even integer. Correct or not? How to get even integer? You just multiply 2 to all the integer. 真的，是真的成，是真的，是真的。It's a very honest notation here. It's a very honest notation. Okay, seriously, how do you think of a even integer? 2 times all the integer? Okay. Yeah. So it will be a multiple of 2. Multiple of, if it is n, then it's a multiple of n. Okay or not? So this one is nz. Does it make sense? Should I write down the general set form? What is the general set form? You have 0, you have n, 2n, 3n, and then minus n, minus 2n, and then so on. Okay, seriously, you multiply n to the whole integer. Can you see or not? Can you see the whole integer like hiding inside this set or not? 0 as a coefficient. 0, 1, 2, 3. Oh, sorry. Question? Feel free to ask. Feel free to ask. Because maybe your question is your classmate question. So we can settle together. Okay, understand all the notation or not? Okay, one hard part about this course is about notation you need to learn. Okay. Can understand notation? Understand? What am I writing here? Yeah. So this one, I do the half definition here, so I need to put like this. So on, and then so. Good. Right. Like a test. What time is it? 7:94. Okay. 7:40. Okay. So one question here. There's one specific subgroup you can look at inside Z. Let me write it down. So what do we do here? We fix, okay, we fix R, okay, to be non-zero natural number. And then we set X to be anything. Okay. What do we do? We take a linear combination, all the linear combination of these two numbers here. So can you see that this is a generalization of the NZ just now? Because if my S is 0, it's just a multiple of R. Okay, it's just a multiple of R. But let's say we have two non-zero Rx here. Do you agree that this is a subgroup or not? Do you agree? Is identity there or not? How to build 0 here? Remind you, you need to be careful. Here is not angle bracket, so it's not by definition there. So this is just defined as set. But I claim that this is a subgroup. So you need to tell me how you generate 0 using this set definition. Right? Let's say R is and X is non-zero. How to generate? How to get 0 out of this form here? How? 加一减一 who 加一 who 减一 R and X no. Okay, so this you need to fix R and X first. Fix R and X first. Okay. So this R and X already fixed. You cannot pick one. What you can pick is N and M, because this linear combination true for all combination. Linear combination. Okay. So how do you build 0 here? R and X is fixed already. 什么意思？有号码，你随便你喜欢的。Let's say R, for example. Okay, I mean you need to read these quantifier. For example, you can take what? R equals to, let's say 2, X equals to, let's say 5. Okay, and then we can form this set here. So example, this set will look like 2N plus 5M for all NM, like this. Okay, so whenever we say for this one, that means we fix for some R and X first. Okay, so for example, this guy here, how do you build 0? Okay, you can, in this case, you can pick -5 and 2. Meaning what? Meaning what? Meaning for generally you just pick, so let's say proof for subgroup. So general you pick what? N equals to -X. So pick N equals to -X. M equals to -R. Or just R is enough. Okay, just I know. Good. But I claim there's the easiest way. N and M is in Z. Keep both of them to be 0. Easiest way. Okay, easiest way to get. Correct or not? I don't care what is R and X. It always work one. Okay, M and N to be 0. Okay, or pick n equals 0, then we can see that. Then we see that 0 is in H. Okay. And then you need to do closure. Closure easy or not? Let's say you have two numbers in this form, right? So consider n1 r plus m1x and n2r plus m2x. What do you need to do? You need to add them together. Is it still in some form, linear combination of r and x or not? Because you can commute, right? And then you can do distributivity. Okay, so in the end, what do you get? Blah, 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 you will get what? n1 plus n2 times r plus m1 plus m2 in x. But we know that integer is closed under addition. Inverses. We do inverses. So consider. So consider. Sure, good. So consider, let's say nr plus mx. What's the inverse? Then we see that nr plus mx plus what? Should be minus n times r plus minus m times x. Should be 0. Okay, and then you need to check the other direction. Okay. Does it make sense? Okay. So similarly, you need to check the other direction. So that's you should get here. Copy. Okay, cool. So this is a subgroup. But my question to you, just now we proved what? Every subgroup of a cyclic group is cyclic. So who generates this guy? Generate this set here. What's the generator of this set? Yes. No, it should be cyclic. So only one guy should generate this group here. One element, not one. Wait, simply guess one. If you say 1, 1, 2, you need to prove it. But you need to imagine this set will change with r and x. Change with r and x, this guy. Generate this guy. In number theory, you guys learn something or not? Like data number theory? Discrete math don't have number theory. Divisibility. What guys you learn after divisibility? Like what? Like what? Like GCD. What's about GCD? Like McDonald? MCD. GCD. Yeah, GCD. What's about GCD? What's about GCD? What's about GCD? So my claim here, this thing is generated by GCD of R and X. Okay, this is generated by GCD of R and X. What's the theorem we use here? Maybe we should recall this in chapter 0. 里边又布置了一个工作。Okay, so let's spell out what we need here. So by corollary above, we know that H must be cyclic. Must be what? Must be a multiple of some integer. But what's this n that generate this linear combination of R and X? Okay, so my claim is this n here is in fact the GCD of R and X. Okay, GCD of X. Okay, so let me tell you why. Then in future we should recall the theorem. So not that what GCD of Rx will divide R, and the GCD of Rx will divide X. So it will solve a Diophantine equation, right? Diophantine equation, okay, which is NR plus MX equals to K times GCD of Rx. Maybe you don't learn the general statement. What you learn should be the Euclidean algorithm. Euclidean algorithm, huh? Okay, let me do some example of Euclidean algorithm for you. So for example, what? Let me see. Let's find the GCD between 8 and 22. Okay, find the GCD between 8 and 22. What do you do? You just divide 22 by 8, right? And then what do you do next? 8除6，然后呢？ And then 6除3 sorry 6除2 and then stop, no remainder already, right? So this implies what? 2 is the GCD of 8 and 22, but you haven't quite seen this guy, huh? How do you see this kind of thing? You do the extended Euclidean algorithm, so you work backward, so such that you can express 2 as a linear combination of 8 and 22. So how do we do this? So 8 equals 2 equals to what? So we work backward, extended Euclidean algorithm. So 2 equals to what? You start with this guy. This can express 2, right? So let's draw some arrow here so that you know where I'm coming from. 8 minus 1 times 6, which is 8 minus what? 22 minus 2 times 8, which is 3 times 8 minus 22. So this is writing GCD as a linear combination of 8 and 22. So you can think of this 8 and 22 as the R and X. And then you can try and get the other linear combination. Okay? Okay. I think I will list out the general theorem things to recall for you. Okay, I think this is a good place to stop. Any question? Question? Which one? Which one? A, G, C, D, R. Oh, hey, why my word gone? Hey, what happened? I think I accidentally moved stuff. So this one is GCD of Rx for some K. Okay. Okay. Okay, so let's break until X02. Zhen完了，是太保。什么？哎，我们去吃那个尼拉耶，好吃啊！哎，他是福州人哎，是哎。呀，怎么？
不能做。
对呀，我就是在讲这个啊。你在做这步的时候，你就是在用我们的 ChatGPT 没有这个东西，因为这是 A， 但是这个是 A， 我就想你在用 ChatGPT 没有这个东西，不要点名啊！哎，你不要点错名哦。
对呀，那你
你讲啊，你讲真啊，你不要点错名
100分，点错就没有啊。
一错就
那我
哦，
我先了，我先了，我点了。
那我 explain A B。
对，
不要跑走啊，这种。
他们要去厕所嘞，给他们去厕所先呢，他们会回来的。
但我每次看到其实第一个
里面你说里面
为什么我第一个反应是这个呢？因为我每次打字的时候为了避审我都这么打。所以下次为了避审，我直接打红笔。
生什么病？生什么病？病。
我还跟你讲那个什么
Epsilon delta and then 对啊，你不知道他 commute 的。
然后说是一小病。
有没有讨论功课咯？花半个钟。好像好。
耶！
这挺难看的，挺有个性的。对啊，是因为好，
那边简单一点。
对，我建议他没给他
这个是不是那个男生 detect 那个韦泽？
韦泽是
那个
对，哎，
没有来，
有我看
好像是哈，
那个这边这个
那里
韦泽
那两个人
这边韦泽这边，来这里看到韦泽没有点名。
这个是不是那个青色衣服那个最后第二排的？
啊，对啊，那个
超级还有，就这个人好像刚来两个，
没有，我看到他有看过。
快进来了。
你真的认完你整班人？
那你啊，那个打赌，
我不觉得。哎，你这样子你会害我认不出你们班人了以后。
就是问你，我不有来没有？我看他班哦，在那边有看到，
这里有。
还是小编。
我写一下认你们班人。
王芳宇没有来咩？我没有看，没有看到。
我拿下。王芳瑜也有，王芳瑜是男的女的？
男的。
王芳瑜也有。OK。哎，讲我分到几点了？忘记了。哦。
8:02。
哦，不对，0啊。
应该可以红色。一个是你的朋友，就是你的学生，一个是那，你是带朋友来？
是。
他
漏掉的我在友军没有来，
没有看到。他早上也是没有来上课。
没有来了几句了。刘金鹏，对啊。
北方会热的，北方要我知道。
要说你的那个我是旁边你就
给我一遍，给他们一个或者但是，就像我要说的，
是的，
所以我又没有所以。这么说，自己说，我知道那个是
太近。
因为我经常看市场的思维分析，你们在性质是会越来越少，然后付出扩展到4元数的时候，已经交换率没了；它扩展到2元数的时候，进货率没了。扩展到3大类的时候，它性质只会更少，很多事情就是说。我就说那个问题有人家讲我们就是说他两个就反正他就懂知道就知道那个点是在前置，好的，
反正我们他没有用，所以不用解，让他们自己去挖发掘。啊，你要啊？你要这本本咯？这是 physics 学生送给我的。你要哪一个？啊？请他们吃啊。
非常巧。
你也能看到的。
我了。
可以看屏，看屏。没有说你，
我俩站着一个是今天我记下来，应该我要开打。
有找资料就是有找资料，
不知道啊，我们那一张
你是说有些有找资料？
没有，就是2道题。
我没有看。没事，你找资料也不用紧，没有问题。
我现在就不是。
Hello, testing. Okay, so so I think we will go on for half an hour, and then we will discuss our assignment later. Okay. Then after assignment, if you think that I marked anything wrong, then you can come and ask or discuss, or you can claim mark if I calculated something wrong. Right. Okay. So what have we been? What have we been? So we have introduced groups and subgroups. Okay. Now we're gonna look at the maps between groups. Okay. Function between groups. Okay. So this function is very special. We want this function to satisfy some property that can preserve group structure. Okay. So I will put down the definition first, and then we will discuss what does this map do. So now we're gonna study the relation between two groups. Okay, let's call it G star and G prime brilliant star, also star, another star. Okay, 5 star. So B groups. Okay. Then we'll define a map called homomorphism. Okay, homomorphism. Have you learned about homomorphism this word before? Homomorphism. No? No, don't know. Okay. So what is a homomorphism? Homomorphism is a map from G to G prime. Okay, it's a map. So it's a map of set. Oh, okay, it's a map of set. In particular, you need to tell me where all the element in the domain have to go to the codomain, such that what? Such that it satisfies this very important property. What's this important property? If you consider a product in your domain space, okay, and then you send it across, what do you expect? Okay, you should expect that it is the same product of phi A times phi B in the new space, in your domain, codomain space. Okay. Meaning what? Okay, if you want to see where this product AB go, you simply just need to know where A and B go. Don't know yet. You don't know yet. Later I'll show you how nice it is. Okay, you don't know this yet. So there's another way, another convenient way to write this. So we turn it into we call this commutative diagram. Okay, I'll draw it for you. So commutative diagram is a very advanced tool you should learn. In particular, this is very important for future ME, such as algebraic topology. Okay, so what is this commutative diagram here? So you could consider so you should consider 4 spaces here. Okay, 4 spaces. 4 spaces here, G cross G, G prime cross G prime, and then G and G prime here. Okay, we're gonna make a square out of this. Okay, how do we make square here? So what can you consider here? You can map G cross G to G prime, and you can map G to G prime using our phi here, our homomorphism. And then how do we finish out this square here? We can put this downward arrow here to denote what? The product operation. Okay, for example. So what does this map doing here, this square doing here? So to tell you about function, right, I need to tell you where the elements go. Okay, so we need to start somewhere. Where do you think it's sensible to start? Where do you think it's sensible to start here? G cross G, okay? If you think of this arrow like a water flow, right? It should flow from here and then to the bottom. Right. Okay. So let's start with G cross G here. Okay, again, product set, we defined last time product set here. So we should take 2 elements inside this product set. Okay, sorry, 1 element. But this pair here, 1 is coming from each G. Okay, so if you send across, what does this phi do to this product set? It's just simply applying on each element like this. Okay, still in a product, still in a pair form, right? Because this is a product of G prime. But if go down, what happens? If we go down, both go down at the same time, what happens? AB will get sent to A cross B, and then phi A, phi B will send to phi A star phi B. Correct, phi B. Phi B. And not SHE. Okay, but we have one more arrow to do. Okay, one more arrow to do. So this phi here will send A star B to where? Send to where? Just phi A star B. Okay, so by right, a priori. Okay, a priori, you guys see this word in the assignment, right? A priori 就是华语什么我不知道怎么翻。有人知道 a priori 的华语怎么翻？ A priori meaning there's without any assumption, without any assumption, okay? They don't have to be the same. Okay, they go through 2 different routes. Why they have to be the same? But if phi is a homomorphism, we require these two roots coincide. Okay, then we will call this a commutative diagram because two roots coincide. Okay. So what? Whenever you see this kind of equation, right, or the equation involving some map or operation, you should think if you can translate it into some commutative diagram or not. Okay? You should think about this. So whenever I see this equation, actually this commutative diagram come out in my mind. I don't just think as one equation, but there's a whole diagram appearing inside my mind. Correct or not? Because this diagram will encode everything that homomorphism needs. You have phi, you have G, and then you have composition. This is actually the whole definition already. If you just look at these, not quite, right? I don't know what G is. Okay. Or I don't know what G prime is if I didn't write all these things out. But this diagram will include all the details you need. What is the domain? What is the codomain? Okay, what's the product in the domain? What is the product in the codomain? And then the most importantly is the last equation here. Okay, so these two roots should agree. Okay, no? Okay, so this is a good way to think about homomorphism. Actually, you have seen these homomorphism examples already. Okay, already you have seen these examples. So let's give some examples. Coordinate. So for example, determinant. Okay, the determinant you learn in LA is a homomorphism. Why? Homomorphism from where to where? GRNR is an invertible matrices. What is the determinant? It's non-zero, which is the multiplicative group of real number. Correct? Okay. So why is it a homomorphism? What equation you prove so that it is a homomorphism? Determinant of AB equals to determinant A times determinant B. Correct or not? You turn the product inside the matrices to a product in a real number. Determinant is a homomorphism. Okay or not? Does it make sense? Okay. What else? You also can show that actually the sine function that we define from Sn to where? Plus minus 1, right? If it is even permutation, then it is plus 1. If it is odd permutation, it is minus 1. But does it satisfy that sine of, let's say, sigma tau is equal to sine sigma sine tau? Is it true or not? Think about it. Is it true? If it's even, odd, even, odd, even. So try and verify this. Okay, verify yourself using the theorem we have proved last time, because of the invariant theorem we proved, right? If your sigma can be expressed as an even permutation, then all the other expressions should be a even permutations. Okay, what else? A very easy one, exponential function. Okay, this one high school already see it already. From where to where? From R, let's say, to R cross. Why? Because you know that e to the x plus y is what? Ex times ey. Okay, so the addition in your domain become a multiplication in your codomain. So these are homomorphism, natural thing inside your life. You have been using this property a lot and a lot. Okay. And then what else? Let's do something else first. So how about this one? Modulus. Okay, modulus. Modulus what? Modulus taking on a complex number such that you will get the length. Okay, why is it a homomorphism? If you take two complex number together, What does this imply? You simply just take R1 dot R2. Okay. Okay. Here now. Okay. So the multiplication inside your complex number turns into a multiplication inside your real number. Okay. There's one more. There's one more, which is this parameterized curve. Okay, parameterized curve from S1 to R to X1, which is I remind you, the unit circle. Okay, let's consider the unit circle with origin 0 in R2. Okay, so how to parameterize this circle here? X going to e to the 2 pi x. Okay. Should we consider at C instead? Let's put in C first. Okay. So this is also a what? Homomorphism. Why? Because if you consider what? If you consider px plus y using plus here. Okay, what is this? It's e to the 2 pi I of x plus y, which is what? E to the 2 pi I x times e to the 2 pi I y. So you are using the exponential property here. But this example is quite important. Okay, in higher level maths. Well, how should you imagine this? R is what? R is a real line. Okay, and then x1 is a circle. So how does this real line interact with this circle? What happened? Actually, what you do is you wrap this circle infinitely many times. Okay, because after 2 pi, you will come back to the same point again, and then you keep going. So can you imagine or not? So you are taking like a string here, you wrap the circle infinitely many times. This is what this map is doing. Okay, from R to X1, infinitely many times. Infinitely many times upward and downward. Okay, upward and downward. This kind of map is very important in your algebraic topology ME. Okay, algebraic topology will learn this. Okay, and we call these covering map. Okay, and we'll call this R as a covering space of X1. Okay, it covered it, right? Cover the circle. Okay, there's a very good application of this, because imagine you are an ant walking around this circle here. 你是一只蚂蚁在这个圆圈上面走。你要记录你走了几圈。You need to record how many times you circle around this circle. Then you will use this line to measure. Okay, if you walk for a period, let's say here to here is 1 round. Okay, and then you can keep going, and then you will get 2 rounds like that. Okay, you get what I say? Okay, so if you repeat your circle here, so actually when you run on the field in SMUM, you count yourself round how many times, right? So you should line out all the round here inside a straight line, but you still run in a circle. Okay. So very useful in daily life. You already do covering map in your brain, just that you didn't write it down. Okay, so we make it precise. We make it precise. Okay. Maybe last example before we move on. So how about this example here? Let's fix an element in G. Okay, I define this map as phi A from Z to G. So how do I define it? I simply send any integer to A to the N. Okay, so what this map do here, if you look at the image of this map here, it is the integer power of A. So this is what? So this is what? So we are picking out the cyclic subgroup generated by A. Okay. So I claim that this is a homomorphism. How should I check it? I should prove that phi A of n plus m equals to what? Phi A n times phi A m. Okay. This times here is what? Is the LLC at G here. But is it true or not? Is it true? So let's see what's happened in the middle here. So phi A of A n plus m is what? A to the n plus m. But what is A to the n plus 1? We keep doing this for the whole day today. This is an star am, which is exactly an times phi. Okay, so this is how you check a determinant. Hey, sorry, homomorphism. Okay, yeah, homomorphism. So do you know what homomorphism means? Homo is what? Yeah, sure, gay. Why gay say homo? Why is it homosexual? Same, good. It's meaning same. Homo means same. So morphism is what? 形态. So morphism is English says what? Same style, not style. Same. That one is Malaysian English, same pattern. Same, same one. Morphism is what? Morph, 形态. Polymorph, yeah, polymorph is a different. So morph is what? Form, yeah, you can talk about form. Yes, good. Form, okay. So if you have a homomorphism between two groups, somehow they have similar multiplication. Okay, I can multiply here first, and then I send across. Okay, it's the same as I apply homomorphism on both elements and combine together. So you can send across. Okay, so if I use this diagram to tell you is, I can either send across and then combine, or combine first, send across is the same, doesn't matter. Doesn't matter. Homomorphism. Okay or not? Homomorphism. So there's a question inside your assignment 2. Last question. Okay, I said that use the method of row reduction to prove that transposition generates symmetric group, right? Okay, so what's the homomorphism I use there? On one side is the symmetric group. On the other side is what? Is the group of permutation matrix. What are the permutation matrix? So if you look at the transposition inside Sn, by similar to question 2, right? You can write out the permutation matrix. So let's say we call those transposition matrix. Okay, so you can relate transposition in the symmetric matrix to what? To the transposition matrix. Okay, does it make sense? Okay, so you imagine I have a permutation. Okay, in Sn, what can I do? I can associate a permutation matrix. Of reduction, do what? You can row reduce it to identity matrix. But imagine inside row reduction LA, you need to recall your LA. How many types of row elementary row operation? 3 types. What are the 3? Row replacement, scalar multiple of one row, and then swapping. I don't know. What is swapping? Interchange 2 row. What's interchange 2 row means? Transposition. Transposition. Okay. But you imagine our permutation matrix. What's the definition of permutation matrix? What's the definition? Permutation matrix. What could the entry be for permutation matrix? Only 1 and 0. But where the 1 has to be? In every row and every column, there should be only 1, 1. If you want to row reduce these kinds of matrix to identity matrix, what do you need to do? You still need to do row replacement. Do you still need to do scalar multiple? What else do you need to do? Just swap. How many times you swap? For sure, it's a finitely many times because it's an n by n matrix. Okay. So, how about I leave you to think about it? So what do you want to show? You want to show that transposition generates symmetric group. So meaning what? Every permutation you need to write as a product of transposition. If you use a matrix method, you need to show that it can be written as a product of transposition matrix. Or in other words, the product of swapping matrix. Does it make sense? Sonia. Think about it. Still have time. Please think about it. Okay. Still think about it. Okay. Yeah. So why we can simply just do this? Actually, homomorphism is not enough. What we need is what we call an isomorphism. Okay. What is an isomorphism? It's a bijection between the two. So meaning you can go forward and then go backward. Okay, bijectively. And then bijectively, you have this property here. Okay. For the group, the inverse of the group homomorphism is still a group homomorphism. Okay, later we will prove that. Okay, later we'll talk more about isomorphism. But for the purpose of your assignment, you can straight away use that Sn is isomorphic to group of permutation. You can use that. And then you can try and use what you know about LA to prove that every permutation matrix. So what you really need to prove under this isomorphism is every permutation matrix you can write as a product of transposition matrix or the swapping row matrix. Okay. I do recording? Yes. Okay. Okay. We can discuss again. Okay. I want you to think about. Okay. For all these assignments, right? There's a very good reason I don't want to discuss because I want you to do your own research first. I want you to develop a habit of researching. See if we can find the right answer. You should think about these questions already have answer. If there's already answer for this question, you still cannot read the answer or understand the answer yourself, then you cannot do research. Because research is about unknown. You cannot find answer one. You need to work up yourself. Okay. So I'm training you the ability to do research. Let me tell you, for now I got in total 7 FYP. Okay, 5 of them is from 2209. That was the first batch I teach MAT 2209. They follow me until now. And 5 of them do FYP, and then all of them do different topic. And they are very independent. Okay. No need to 老师手牵手的。做这个做那个做那个。Let me tell you, the other lecturer is really 手牵手。I don't. You go and pick out yourself. I don't know. You tell me next time. Okay, but anyway. So 我们没有手牵手我们是非常独立的。Okay. Thank. Okay. Right. Okay. So we need to learn to be independent doing research. Okay. 我们是 adult 不是小孩。Okay. Focus on this. How about we prove one proposition before we discuss assignment? Do you still want to prove or not? Okay, ask the other first. still want to prove proposition or you want to discuss assignment? Huh? What did you say? Assignment. Assignment lah. Okay lah, we do assignment lah. You guys very excited, is it? Assignment lah. Assignment. How about the rest? Okay, let's do assignment lah. Okay. Let's do assignment. Where is it? Where's my assignment? So please open out your assignment now. It's on the Moodle. Go and open out. I already give feedback to you. Open your open out your assignment. Okay, I will tell you how I take off mark and what I want you to write inside. How you write your assignment. So you know why you get deducted. So you maybe will see that my solution is different from yours. So I hope that you can learn. Okay, please learn the way of writing, okay, from my solution. It's not that I want you to copy exactly, but the format, okay, roughly, okay, you should follow. So our first question is about matrix multiplication. Matrix multiplication for n by n real matrices, okay, is associative. I think most of you know how to do it, but just some of you are not using formula or what. But the key point here I want to look for is this line here. This line, the key point I want to look for is this line. Seng's finite sum commute. Okay, this is the key point. Okay, even if you write equal, you don't write the reason, I still take off your marks. Okay, I will be little strict this first few times because, sorry, I want to how to say, I want to signal you what you need to explain clearly. Okay, because this is how you should communicate with people. But the key point is this one. If you don't put this, I just deduct 2 from your full mark. And if you write down the rest, if you don't write the rest, it's okay. Okay, but it's better you write down step by step. By what. Okay, I think Rayshaw use this kind of thing, right? Inverted dot. Okay, some of you use inverted dot. So I think in our class, maybe we'll ban this. Okay, we'll ban using inverted dot or a proper triangle dot in sequence. Okay, we don't want to see this. Okay, please replace this as, like, for example, you should say since or what, as because and then what else or hence is for the answer, right? Hence therefore what else? Thus, what else? So good. Then also can. Yeah, quite a lot to use huh? Because I know why some of you in particular some of the Chinese students not racist but because seriously I was a tutor in Australia. Okay, the Chinese students they just write like this. I asked them hey, why you guys like to write like this You know what they say? Yes, Gaokao. They said not enough time to write in Gaokao, so they just have to Okay, so I will make sure you have enough time to answer in my class. So please don't use this . Okay, so don't use this . Okay, yeah, it's really cannot recognizable you see, if you put them together. So avoid using them avoid using them. Okay, any question on question 1 or not? Everyone okay with the formality you need to answer? Any question that you want to ask about this question? The step. How is it different from yours? Yeah. Oh yeah, about this showing one line thing. Why? Okay, excuse me. Why when I show all the equal, meaning the n equals to the other n. Do you know why? You know what am I using here? I'm using transitivity here. If A equals to this one equals to this one, 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 then A is equal to the last thing. Okay, not. So I'm really using the equivalence relation property here. Okay. Some of you like to, okay, later is the other question clearer. So how about second question? Actually, you can ignore this notation and next time I'll remove this. I forgot why I put this last time. So second question is about proving left identity and right identity agree. Some of you talk about identity. Yeah. Do you know what's the difference between left identity, right identity, and identity or not? Identity includes both static condition in the left and right. Okay, so left and right somehow split the condition for identity into two. So we need to see left multiplication and right multiplication. Okay, and then you need to show that they're equal. Okay, why are they equal? You simply look at the, what is this? Left identity times right identity. Okay, so some of you write your argument like this. Okay, you write your argument like this. So you say that E1 equals to E1 star E2 star, and then so not that, and then E2 equals to, what is it? E1 star E2. Since E1 star E2 equals to E1 star E2, E1 equals to E2. Anything wrong with this? Sounds a little bit funny. Funny is not because of these two are equal. Funny is because this implication here. I seriously can't see. Sorry, this is E2, right? So I seriously can't see E1, E2. So what? I seriously can't see E1 equals E2 from here. I cannot see. 好像没有头没有尾的，你懂吗？ Because E1 equals to E2 really come from these two lines. The above two lines is the one that give you E1 to E2. Not because these two are equal. Obviously, these two are equal. Hey, you don't laugh. Hey, you don't laugh. Don't laugh. Next time, is you who are writing this kind of statement. Okay, don't laugh. Okay. So, whenever you, okay, now you are in the transition from calculation to argument. So, when you do argument, we care about connectivity between phrases or statement. Okay, so you need to tell me why since this, then this. Why make sense? Why? Actually, it's because of the two line above. So instead of putting this line, you just put these two lines. Since these two are true, then the bottom true, then done already. Isn't it clearer? Oh. Okay, so this is a difference between doing calculation max and proof max. Okay, we focus on how we argue our point. Hey, sorry, yeah. Sure, but yeah, it's not wrong. It's not wrong. Still okay. It's not wrong. In mathematics, if you write down something maybe look trivially true, it's still okay. But we hate something that's not connected. We hate that. What? Oh, later I will explain that, I think. Oh, okay, I can do that together also. Okay, so well, there's another kind of people is another type of answer is that says that E1 star E2 equals to E1 equals to E2. So what's wrong with these? If you already proved that, then it's okay. But for proving type of max, we always see equation as a sentence. So meaning what? There's an order in this sentence. What's the order in this sentence here? I know that E1 star E2 is E1. And I also know that E1 equals to E2. But you are trying to prove E1 equals to E2. You haven't proven yet. But what you are using is, I also know that E1 star E2 is also E2. Only then, okay, only then you implies that E1 equals to E2. This is using transitivity. Okay. Otherwise, if you just put it at the back, it's like there's some other reason I know why it is true. Then what's the reason? You get what I mean? Yeah. Okay. So we read equation. It's not like backward, forward, backward, forward. Although we can read it backward, forward, but we read it as a sentence. Okay. Does it make sense? Okay or not? Okay. So if you write it at the back, it seems like you have another reason. Why this is true? I still don't know. Okay, unless I know that, oh, E2 is equals to E1 times E2 also. So by transitivity, we know that E2 equals to E1, which is E1 equals to. Okay or not? Okay. Right. So this, I think these are the two main problems for this question. Oi! Oh. I forget to remove this solution. Never mind. So this last question here. So what do we do here? Okay. So this question says that you start with a G with an associative LC and identity. If what? 做喂，不要推我哦，会被警察抓的呢。Okay, if delta square is invertible, then delta is invertible. Okay. Okay, so you assume that there's an inverse for delta square first. Okay, and then you want to find inverse for delta. There are various ways to approach this question. You can directly show the inverse for two equation, or what do I do here? Since I already know that m delta square equals to identity equals to delta square m, I can use associative to see that actually m delta times delta equals to E and delta times delta m equals to E. But to be an inverse of this delta, what do you need? You need to have the same guy applying on both left and right to get identity. Okay. But here, what's the difference here? One is m delta, the other is delta m. So if you can show that they are the same element, that means what? The same element that apply to left and right will give you identity. This is exactly the inverse. So you just need to show that m delta equal to delta m. Okay, then we'll finish the job. Or some of you just go and check. Okay, maybe you set my inverse is m delta. Okay, and then you check whether m delta times delta get E or not, or you check delta m delta you get E or not. It's okay, that's fine. But in the end, somehow you need to go through this kind of calculation, for sure. Okay, for sure you have to go through this kind of calculation, showing that m delta equals to delta m. It's hidden in your step if you try and figure out. Okay, it's hidden in your step. Okay, similar things here. I think there's one very good thing done by Ratio. Can I pull your assignment out? Do you mind or not? Okay. So there's one extra thing done by Ratio. Let me show you. So Ratio, he did this not here. This is exactly the point I want to ask for this question here. So the finite condition here is very important for the finite sum to commute. Otherwise, you can see that the associative might not work. Okay. If you consider infinite matrices, maybe it might not work already. Okay. Yeah. If you consider infinite matrices. Okay. Associative might not work. This is the exact point that I want to ask in that question, because the finite sum commute. If it is not finite sum, no matter how you commute, maybe you have some counterexample. Okay. So he showed that if you set A to be matrix with all one, C with all one, and then you put this tricky B in the middle, and then you can see it is not associative. Okay, so exactly the main point that I want to ask in that question is the finite sum commuting. Okay. Any question before we? No, not yet dismissed. I want to share about the result analysis first. Let me find. I want to talk about the result analysis first. Yes. Where is it? Yeah. What's going on here? Shit. Okay, never mind. Okay. I think it's not outdated in my file, but I can talk about it also. So I think although this is the first assignment, but also from your class performance, I think so far this is the best MAT class I have met. Okay, the best MAT class. I'm not trying to spoil you. Best MAT class. So I hope you can keep your performance. Okay, for this assignment, right? If you're under 10, 12 or and under, you are considered performing not good. Okay, so you need to improve. Okay, you surely have to improve. Okay, otherwise you will left out even quicker. Okay, so you need to improve. So try and come to office hour. Okay, and then how good is your class? I want to talk about this. So the average is around 77%. And this is not the best about this average here. Your class has a fierce competition because the standard deviation is 3. Okay, standard deviation is 3. So far, I think I never met this kind of standard deviation before, because usually they will have very separate, like good people is really good, weak people is really weak. Okay, so this class is, I would say, above average. Okay, above average, at least from assignment 1. Okay, so I think you guys have to work really, really hard. Otherwise, you will be taken by the others, by your classmate. Okay, otherwise you will be taken by your classmate. So which is good, because I also can feel that you guys most of you, I cannot say all of you, but most of you can follow my lecture. Okay, this is not an ordinary phenomenon actually, unfortunately. But I can assure you, if you can follow me, no need to say 100%. Most of the time, for 15 weeks, surely you will be different than the others inside here, inside SMU. Also inside here, your brain will be different. Okay or not? So please follow closely. Okay, I will bring you do something that you can't imagine. Okay or not? Okay, so actually there's some top scorer here. I mean 90 to 20. I don't have name with me now. I think there's around maybe 7, 8 of them. Okay, actually quite a lot. And then yeah, quite a lot. So please work harder. Otherwise your classmate will take over you. Okay, please work hard. Okay. Any question? Any question? No, so let's try and work out your assignment first, and then if not, we will discuss again when should we extend on Thursday. Okay, no? Okay, I try and work out first. Try and push yourself first. No need to push until you go and 跳楼啦. That's too extreme. Okay, too extreme. 不要动不动就跳楼，好不好？我都不想跳楼了，你知道吗？我都还没有跳，对不对？ 不要跳 ，OK， 跳楼不是解决方法，过来跟我讲就好了 ，OK 了吗 ？OK， 不要去 confession 跳楼啊，OK， yeah. So we can discuss one, okay? We are adult. Discuss is keen. Okay, must discuss. Okay, so see you on Thursday.
周二。